Hello dear students, welcome to the class of Electrodynamics 1. In this class we will discuss the monopole and dipole terms, physical dipole and pure dipole, origin of the coordinates in the multipole expansion, the electric field of a dipole. At first we discuss what are the different kinds of the poles. The monopole is a single charge and its potential depends upon 1 over r, where r is the position of the field point. Dipole contains the two opposite charges, negative and positive charge, and these two charges are separated by very short distance, and its potential depends upon 1 over r square. This is the quad pole. Quad pole is made of two dipoles which are in front of each other, and its potential depends upon 1 over r cube. This is called the octopole. The octopole is made of two quad poles. This is the one quad pole and this one is the second quad pole. These two quad poles are in front of each other. So octopole potential depends upon 1 over r4. In the previous lecture we discussed the potential due to the charge distribution and here we revise again the result of the previous discussion, and then we will discuss in detail the monopole and dipole terms. So this term is called the monopole term, and this monopole term depends upon 1 over r, and this term is dipole term, and this dipole term depends upon 1 over r square. So let's discuss the monopole term in detail. The monopole term is Vr is equal to 1 over 4 pi epsilon naught 1 over r integral rho r prime theta prime. This monopole term can be written as Vm mono is equal to 1 over 4 pi epsilon naught q over r, where this q is integral rho r prime theta prime, because if we integrate the volume charge density over the whole volume, we get the total charge enclosed in that volume. If the total charge is not zero, the dominant term in the potential is monopole term. And if the total charge is at the origin, other term will vanish. If we expand the potential by using the multipole expansion, the multipole expansion contains the many terms such as the monopole terms, dipole terms, quad pole and octopole terms, and so on. If the charge is placed at the origin, in that case all the other term will vanish and exact potential is due to the monopole term. But if the charge is not at the origin, in that case the potential exact potential is not due to the monopole term, then other terms must be included to get the exact potential. Now we discuss the dipole term. Dipole term is V dipole at r distance from the origin is equal to 1 over 4 pi epsilon naught 1 over r square integral r prime cos theta prime rho r prime theta prime. If the total charge is zero, and the charge distribution contains the positive and negative charges. In that case, the total charge becomes zero, and then the dominant term in the potential is the dipole term. And this is the charge distribution, and this is the field point. We divided here this charge distribution into a small volumes, and each small volume is denoted by delta prime, and its position with respect to the origin is denoted with the r prime, and field point is separated from these source points by this r, and this r is the position of the field point. So here the theta prime is the angle between the r and r prime, and the direction of r is along this arrow. So we can write r prime cos theta prime, which is here. We can write this is equal to r cap dot r prime, because when you will expand it, the magnitude of r cap will be equal to 1, and magnitude of r prime will be equal to r prime, and angle between these two vectors is theta prime. So this will be equal to r cap cos theta prime. So we can write the above dipole term here in this way. V dipole r is equal to 1 over 4 pi epsilon naught 1 over r square. Here you replace the r prime cos theta prime is equal to r cap dot r cap. Plug this into this equation and you get this one, r cap dot integral r prime rho r prime theta prime, where this integral r prime rho r prime theta prime is called the dipole moment, which is denoted with P and is defined as integral r prime rho r prime theta prime. And plugging here the dipole moment, we get the dipole moment potential due to the dipole moment, that is V dipole r is equal to 1 over 4 pi epsilon naught P dot r cap divided by r square. So this is the potential due to a dipole. Now we discuss the electric dipole moment. Previously, according to the definition of the dipole moment, we had written P is equal to integral r prime rho r prime theta prime, where r prime is the position of source coordinates and theta prime is the small volume element of the charge distribution. For the discrete charges, this dipole moment can be written as in this way: P is equal to summation I is equal to 1 to n qi ri prime. This I depends upon the number of the charges. If there are the n number of charges, then we will take the summation from 1 to n, and these terms will become P is equal to Q1 R1 prime plus Q2 R2 prime plus Q3 R3 prime, and so on. This is the dipole, and for this dipole, as shown in the figure, we take the origin here, and dipole moment of this dipole can be written as P is equal to QR prime plus minus QR prime minus. What is the R prime plus? R prime plus is the distance of plus Q charge from the origin. And what is the R minus prime? R minus prime is the distance of minus Q charge from the origin. And if you take common Q, then you can write Q is equal Q into R plus prime minus R minus prime. And the distance, because the whole distance from plus Q charge to minus Q charge is d, and the distance from the origin to this plus Q charge is the d by 2. So we can write the coordinates of plus Q charge. If you take this line along z-axis, then coordinates of plus Q charge are 0, 0, d by 2, because the distance of plus Q charge from the origin is d by 2. And similarly we can find out the coordinates of minus Q charge, because minus Q charge is below the origin along negative z direction. We can write its coordinates 0, 0, minus d by 2. So putting here the coordinates in the place of r plus prime, r plus prime is equal to 0, 0, d by 2, and putting here in place of r minus prime 0, 0, minus d by 2, and we get is equal to q 0, 0, d, because this will become plus, minus minus become plus, and d by 2 plus d by 2 will be equal to d. And so we get the dipole moment of this dipole is equal to qd. Between the physical dipole and pure dipole, you know that for any charge distribution, potential can be expanded in terms of many poles, such as the monopole term and dipole term and quadpole term and then octopole term. So any charge distribution contains the monopole, dipole, quadpole, etc. But in case of dipole, which is shown in this figure, we have considered only its dipole term, and potential due to this dipole term is approximate, which is this, as we have derived this potential in previous slides. This potential is derived from this second term, V dipole is equal to 1 over 4 pi epsilon naught P dot r cap over r square, and this potential is approximate, and we call it equation A. This is approximate because the other terms are not included. Obviously the first term goes to 0 because net charge is 0, but third, fourth and fifth term may not be 0 in that case, so this potential due to this dipole is approximate, and such kind of the dipole is called a physical dipole, for which equation A is approximate. But a dipole is called a pure dipole, for which equation A is not approximate. And for a pure dipole, this equation would not be approximate only for the case if it fulfills the condition that d approaches to 0, q approaches to infinity. D is the distance between the positive and negative charge, and q is the magnitude of charge of this dipole. and we call this condition name B, mean that the Q approaches to very close to minus Q charge, and magnitude of charge also become very high. In that case, this equation A would be exact. So we can say that for the good approximation of equation A, physical dipole must approaches the condition given in equation B for pure dipole. Here we describe the direction of a dipole, and a dipole is shown here, which consists of positive and negative charge, and its direction is from negative charge to positive charge in upward direction. And quadpole is shown here. Quadpole consists of two dipoles which are in front of each other. The direction of upper dipole is from left to right, while direction of lower dipole is from right to left, and net dipole moment of quadpole is equal to 0. Or we may consider it in this way: left dipole as well as right dipole. Direction of left dipole is downward, but the direction of right dipole is in upward, and so net dipole moment is equal to 0. And potential dominant potential is due to the quadpole moment, which is the third term in case in the multipole expansion. First two term goes to 0 because first term goes to 0 because total charge is 0, and second term goes to 0 because the dipole moment of the quadpole is 0. So dominated term is the quadpole term, and because the quadpole moment is not 0 for this term. Now we look at the different next topic, which is the origin of the coordinates in the multipole expansion. For this we take a coordinate system, and charge Q is placed at the origin. We call it a monopole. But if the charge is displaced from origin, then it is not a pure monopole. And multipole expansion depends upon the coordinates of charges. If the charge is at the origin, then it will be a pure monopole, and multipole expansion will consist of only one term. Mean first term will be exact potential in the case of monopole. But if it is not a monopole, then it will not then it will require the all other term to be expanded. So if the charge is at the origin, the monopole potential is this, and we call it equation A. But if the charge is displaced from the origin and monopole potential is not quite correct for this configuration, and exact potential is this, 1 over 4 pi epsilon naught q over r. Remember that these are the two different r's, and this r is the field point position, and this r represent the separation between the field point and source point. So in the case of monopole, the potential can be written as in term of this r, and but if it is not a pure monopole, in that case the potential can be written as in this form. In this form, then it is necessary to expand this 1 over r term. So we will see in the next slide how we can expand it. Here we are very much interested in the dipole moment of a single charge. Is a single charge have any dipole or not? Does a single charge have a dipole or not? Yes, a single charge can have a dipole and it has the dipole moment, and dipole moment can be calculated using this equation: summation I is equal to 1 to n qi r I prime, where ri prime is the position vector of charge qi, and position vector of charge qi q is the d from the origin, and can be written as p is equal to qd, and its direction is from origin to point q, means in the direction of y cap, so it can be written as qd y cap. If charge is displaced from the origin, in that case monopole potential is not an exact potential, and we have to expand 1 over r. 1 over r mean this r, as we have discussed in the topic of multipole expansion, where we have expanded this 1 over r is equal to 1 over r summation n is equal to 0 to infinity r prime over r raised to power n pn cos theta prime, where pn is the Legendre polynomial, and this n extends from 0 to infinity. For n is equal to 0, this will be n first term, and this will be equal to r prime over r raised to power 0 mean 1. This will be equal to p naught. P naught is also equal to 1, so first term will be equal to 1 over r is equal to 1 over r only. For the second term, n will be equal to 1, and this will be equal to p naught p1, and p1 is equal to cos theta prime. In that case 1 over r will be equal to 1 over r into r prime over r raised to power 1 into cos theta. In this way we can expand and we can find out all other terms. This would be a case for when the charge is displaced from the origin. It means that multipole expansion depends upon the choice of the origin of the coordinates. So moving the origin can radically alter a multipole expansion. Now we discuss the effect of shifting of the origin on the dipole moment, quadpole moment. We know that the monopole moment is V mon is equal to 1 over 4 pi epsilon naught q over r, and dipole potential is equal to 1 over 4 pi epsilon naught 1 over r square r cap dot integral r prime rho r prime theta prime. So monopole moment is the charge q and it does not change with the shifting of the origin, because charge q is independent on the choice of the origin. So charge q represent the total charge, so it will not change with the shifting of the origin. So monopole potential or monopole term does not depend upon the shifting of the origin. It is a fixed. But the second term, which is the dipole term and dipole potential, it does depend on the shifting of the origin. So dipole moment change with the shifting of the origin. P is equal to integral r prime rho r prime theta prime. Dipole is independent on the choice of origin for a case when the net charge q is equal to 0. It means all the time dipole moment depends upon the choice of the origin of the coordinates, except for the case when the net charge is equal to 0. Its example is a dipole. Its dipole moment is qd, and this dipole moment is independent upon the choice of origin. Here we prove that the dipole moment is independent when the total charge of the configuration is 0. As we discussed in the previous slide, that dipole moment does not depend for the configuration which total charge is equal to 0. So to prove this, we consider this figure. This figure has two coordinates system, two different origins, coordinate system which has the two different origins, and for this we consider a small volume element theta prime, and one reference point is this and other reference point is this, and position vector of this source theta prime with respect to reference point 1 is denoted with r prime vector, and position vector for the source theta prime with respect to origin 2 is r prime bar, and position of the origin 2 with respect to origin 1 is a vector a. So we here prove that dipole moment with respect to reference point 2 is equal to the dipole moment with respect to reference point 1. Dipole moment with respect to reference point 2 is denoted with the p bar is equal to integral r prime bar rho r prime theta prime. This is the term which represent the dipole moment with respect to reference point 2. So here we put the value of r prime from the figure, where this a vector is A vector is the component of R prime, and this R prime bar vector is also the second component of R prime according to head to tail rule. So according to head to tail rule, R prime is equal to sum of vector A plus R prime bar. So R prime bar will be equal to R prime minus A into rho R prime theta prime. Multiplying rho R prime theta prime with R prime minus A, we get these two terms, R prime rho R prime theta prime minus A integral rho R prime theta prime. And this term integral rho R prime theta prime denotes the total charge, and which is equal to 0. As we have discussed that we are going to prove that dipole moment is independent for the configuration which has the total charge equal to 0. So this term goes to 0 and only this term remains. And this term is the dipole moment with respect to the reference point 1, because R prime is the position vector of the source charge with respect to the reference point 1. So R prime is here, integral R prime rho R prime theta prime. We can write it equal to P. P is the dipole moment of the source with respect to reference point 1. So hence proved that P bar is equal to P. It means that dipole moment with respect to the reference point 2 is equal to the dipole moment with respect to the reference point 1. It means that dipole moment of this charge configuration does not depends upon the reference point, because total charge is equal to 0. Here we consider a dipole, and for this figure 1 you can give the answer with confidence that its dipole moment is Qd. Why? Because you know that the total charge of this configuration is equal to 0. But for the figure 2, there are the three charges Q, plus Q, plus Q and minus Q, and the question is for what origin? Its dipole moment depends upon the origin. Why? Because total charge of this configuration is not equal to 0. So dipole moment of such charge configuration depends upon the origin. The next topic is the electric field of a dipole. This is the physical dipole. We are not interested to find the electric field of a physical dipole. We are going to find out the electric field of a pure dipole. This is the pure dipole. Has the direction upward along the positive z-axis. We are going to find out the electric field due to this dipole at the position R. This R makes an angle theta with the z-axis. If you take the projection line, which is this, this makes an angle phi with the x-axis according to spherical coordinates that we had discussed in the first chapter. How we can find out the electric field from the electric potential? because we know the electric potential due to a pure dipole in in the previous slides we had discussed. So plugging here the equation of electric potential and taking the gradient of this, we can find out the electric field. The gradient, general formula for the gradient of any scalar potential T is equal to curly T over curly R into R cap plus 1 over R curly T over curly theta into theta cap plus 1 over R sine theta curly T over curly phi into phi cap. This is the formula in spherical coordinates to find the gradient of any scalar potential. Here we are interested to find out the gradient of electric potential V, so we replace this T with V to find out the electric potential. What is the value of V? The equation of V that we have discussed in the previous slides, which is this V dip r theta is equal to r cap dot p over 4 pi epsilon naught r square is equal to p cos theta 4 pi epsilon naught r square, where theta is this angle and r is this distance, which is the position of field point with respect to origin. So we now find the gradient of T. To find the gradient, we must take the partial derivatives with respect to r, theta and phi. At first we take the partial derivative of V with respect to R. V is this, and when you take derivative with respect to R, then theta is constant and derivative of 1 over r square is minus 1 over r cube. So ER, which is the radial component of electric field, will be equal to minus curly V over curly R according to this formula, because negative sign is here. So when you take the derivative of 1 over r, which is equal to minus 1 over r cube, this minus and minus become plus, and you get a positive radial component of electric field 2p cos theta over 4 pi epsilon naught r cube. Now we find the second term of which is theta dependent term, and this is equal to 1 over r curly T over curly theta into theta caps. So we have to take the derivative of potential with respect to theta. Here r is the constant, and taking the derivative of the cos theta, which is equal to minus sine theta, so we get negative negative become plus. So E theta is equal to minus 1 over r curly V over curly theta is equal to p sine theta 4 pi epsilon naught over r cube. Now we find the third term, and third term is 1 over r sine theta curly T over curly phi into phi cap. Here we have to take the derivative of electric potential with respect to phi, and in the equation of electric potential here there is no any phi dependent term. So it means that V does not depend on the phi coordinates. So when you will take the derivative with respect to phi, it will goes to 0, will go to 0, and we get E phi is equal to 0. So after taking the derivative of all these three terms, we get the radial component of the electric field is equal to this, and theta component of electric field is equal to this, and phi component of electric field is equal to this. So to find out the total electric field, we have to add all these components of the electric field. Using the formula of the gradient, and we find the electric field, and adding all the component of the electric field, we get this. You can see here, this one is the 2p cos theta over 4 pi epsilon naught r cube because electric field has the component E is equal to ER into r cap plus E theta into theta cap plus E phi into phi cap. So putting here ER is equal to 2p cos theta over 4 pi epsilon naught, and then putting E theta p sin theta over 4 pi epsilon naught over r cube. You can see here this p over 4 pi epsilon naught r cube is present in both terms, so it is the common, and we can take it common. So E d bar theta is equal to p over 4 pi epsilon naught r cube into 2 cos theta r cap plus sin theta into theta cap. This is the electric field. This is the field of a pure dipole, and this is the field of physical dipole. You can see that the charges of the physical dipoles are much separated as compared to the charges of pure dipole. According to the condition of the pure dipole, when d approaches to 0 and q approaches to infinity, here the magnitude of charges is very high as compared to the magnitude of the charges of the physical dipole. So this is the electric field. This electric field is much higher as compared to the electric field of the physical dipole, where these electric field lines are closer. It means that the electric field is stronger there, and you can see at this position the electric field is much stronger, so as compared to the electric field of a physical dipole. Thank you.